Hello and welcome to Biostatistics in a Nutshell. My name is Pascal and I'm going to be your biostatistics guide for the next 6 weeks or so. What you can expect from this hybrid online and in-person course is a series of recorded lectures that you listen to on your own time, and then you have the opportunity to meet in person or virtually for the discussion sessions. Okay, let's start off with a little fun. So Benjamin Disraeli was a very successful Prime Minister of England in the late 1800s, and he said there are three kinds of lies: lies, damn lies, and statistics. Now, this perception of statistics, it comes from the fact that if you torture data enough, you can get it to tell you basically whatever you would like to say. And so it's our job as statisticians to make sure that the way we report findings and the way we perform our statistics are done correctly and with integrity. Now here's another fun one. So Andrew Lang was a poet, a Scottish poet actually, and he says he uses statistics as a drunken man uses lampposts, for support rather than for illumination. And I think this one points to those of you that think that statistics is just a chore that needs to be done, and something that you think of at the very end of the project. Oh yeah, whoops, I got to put some statistics in here so I can get published. Rather than thinking, well, actually, if I consider statistics all through the process of research, so meaning from beginning to end, that I may actually come out with a much better product as opposed to just as a crutch. Okay, so who recognizes this British lady from the late 1800s? Probably not too many people have raised their hand. However, if I tell you it's Florence Nightingale, I'm sure most of you are going to say, wow, that is the founder of modern day nursing. And you'd be right. However, what you probably don't know is that she also contributed a lot to the field of statistics. And she did so by incorporating management and administration of resources in hospitals, field hospitals, and basically in medicine. And this is how she built modern day nursing. Okay, here's her wonderful quote. Statistics. The most important science in the whole world, for upon it depends the practical application of every other science and of every art. The one science essential to all political and social administration, all education, all organization based on experience, for it only gives results of our experience. So there you have it. Florence Nightingale, a statistician. Who knew? Okay, let's play a game. So Paul Corey has been playing this game with his students at the University of Toronto for many years. And essentially what it involves is you flipping a coin 4 times and then repeating this 1,000,000,000 times. You then calculate the proportion of the 1,000,000,000 games that has 2 heads and 2 tails. Now, of course, in the past, Paul would do this in class, of course, and hand out slips of paper with the 5 possible answers, and you would circle the one that you think is correct. In this case, we're virtual, and so we're just going to ask you to think of the correct answer and hang on to it in your head as we go through the slides. I'm going to give you exactly 1 minute to think about it, and then we'll move on to the next slide. So, ready, set, go! Okay, so that's 30 seconds. You have another 30 seconds to go. What proportion of the billion games has 2 heads and 2 tails? Each trial is flipping a coin 4 times and recording the number of heads and the number of tails. Okay, time's up. Put your pencils down. I'm just kidding. Just think of the answer, hang on to it, and I'll see you in the next slide. Okay, welcome back. So if you answered 0.4, you would be correct. Now, interestingly, this is a sample of some of Paul's results from numerous classes taken over time. And you can see that the most popular result is 0.5 by far and away. And this is then followed by 0.2, and then 0.3 and 0.4 is about the same, and then finally 0.1 is the least popular answer. And so what we're going to go over now is how did we come to an answer of 0.4 in terms of proportion of equal heads and tails. Okay, so every time you flip a coin, you record whether or not you have a tail or a head. And you do this 4 times for each trial. So these trials are going to look like these groupings of 4 letters, or 4 T's or H's. And each one represents a trial. And if you did it a billion times, you'll see that a lot of the trials look exactly the same because they're the same result. And it so happens that if you sort them all, you'll see that there's only 16 possible ways of flipping a coin 4 times. And then if you order them in the number of heads per trial that you get, you'll see that you'll go from 0 heads, so all tails, 1 head, 2 heads, 3 heads, and then 4 heads where you have no tails. Interestingly, what we're interested in is the middle column where you have 2 heads and 2 tails, and this is where you have the greatest number of possibilities or possible ways of flipping a coin 4 times. You actually have 6. And if you look at the number of ways you can get 2 heads and 2 tails over the total possible ways of flipping a coin 4 times, that's 6 over 16, which is 0.375. And if you round that up, it's 0.4. And there is your answer for the proportion of your flips, of your trials, that will have 2 heads and 2 tails if you had done it a billion times. If you didn't get the answer right, don't beat yourself up over it, as most people, as we've seen anyway, through the years, most people guess wrong anyway. Okay, what's next? Okay, what's next is a little funny. So here's an old cartoon, and I say old, but it's not that long ago. It's in the 90s, but it's actually a scan of a newspaper comic strip, which these days you see extremely rarely, if at all. Anyway, so the born loser. Anyway, so the teacher says, can you tell me how much 4 plus 5 is? And the little girl answers 8. And the teacher says, no, 4 plus 5 equals 9. And she says, then let's try again. How much is 6 plus 3? 10? No, 6 plus 3 equals 9. And then the little girl says, wait a minute. I thought you said 4 plus 5 was 9. So what's going on in this comic strip is that the little girl did not know that there was more than one way of getting a sum of 2 numbers that's equal to 9. And in our game, many students did not know the number of ways of getting 2 heads and 2 tails in 4 tosses of a fair coin. So before introducing an important application of this coin flipping result, let's introduce the general statistical model. Suppose we want to compare patients on two different drugs, diets, or exercise programs. Call these exposures. We have N patients in each group. How did they get assigned into groups? Now, one way is to select the data from a database in what is called an observational study. You guys should all be well versed in that. And the other way, subjects did not choose the exposure, but were randomly allocated to the two groups by the scientist in what is called a randomized trial. Okay, before you freak out when looking at this slide, thinking to yourself, whoa, I did not sign up for this course to have this kind of math on slides. Let me explain something to you. So we're teaching you Introduction to Statistics. Inevitably, there is math and statistics. Therefore, we need to include some math in our teaching, just so that we can, back up all the concepts that we're sharing with you. But what our expectation is for you is simply to listen, try and understand as best you can, and then to have on hand all of these slides as a reference so that you can come back to it later if you wish and do the math and go, oh, I get it, fantastic, now I understand, as a tool, as an aid for you as you move along in your statistics education. Okay, so this slide here, we're introducing the concept of a random variable, essentially. And so that concept is obviously very important in math and in statistics, but essentially it's every variable that you want to include in your model will be a random variable. So meaning that even if you were to, let's say, consider body weight, you're going to be drawing body weights from a population of body weights, right? And so if you wanted to then, predict, or if you wanted to know what the probability is of drawing a certain body weight from the population, you would need to know the distribution of body weight across the population. Makes sense, correct? So in this one, because we did coin flipping, we are working with a binomial distribution. And we showed this in the previous slide where we ended up having a frequency distribution of 16 possible trials for when we flipped a coin 4 times and the coin was fair, meaning that there was a 50% probability of getting a heads or a tails. And this is what we're showing here in the math, that if you want to know the probability of, here, let me get my pointer going for you, the probability of drawing 2 heads or 2 tails, of course, from a trial that has 4 flips in B, which is the binomial distribution, then this is the math to calculate the probability which we did in the previous slide, which is 0.375. In this case, this is combination, the combination of when you have 4 flips and you want 2 heads. This is the probability, P, of obtaining a head here. Q is the, basically it's 1 minus P, which is the probability of obtaining tails. In this case, they are equal, of course, because it's a fair coin. This nomenclature is explained here. It's factorial, and it's simply 4 factorial is 4 times 3 4 times 2 times 1. I'm sure you guys have covered that. And so when you do the math, this is how you come to the calculation. If you wish in the future to actually handwrite all of the possible results that can be obtained and do as we did in the previous slide, you certainly can do that. The challenge, of course, is if you get a very large distribution with very many different results, it will take you a long time. So this, obviously, this concept can also, for instance, be applied to the trial if it wasn't a flip of a coin, but a homozygous offspring. In this case, it's recessive, AA, for the heterozygous parents where you have the dominant allele and the recessive allele. If you have this cross, what's the probability of the homozygous offspring, recessive, will be p equals 0.25, and you're welcome to give that a go in the equation above. Now this slide should look familiar to you because we've already shown you the same information but in a different format. So this is the binomial probability distribution for when you have 4 trials, so 4 flips of a coin with a fair probability of obtaining heads or tails on the flip. And on your y-axis you have the binomial probability, and on the x-axis you have the proportion of heads. So this looks exactly like the previous slide, 2-3 slides ago, where you sorted and ordered all of the possible results from your 4 flip trials. And essentially here we've just put it into a graph, and we've put the little bars to represent, for instance, where you have 2 tails, 2 heads. Right in the middle, you'll see that the probability on your y-axis is 0.375. Nothing new. This is just showing you how you would represent it. Okay, so what's different in this graph? It's extremely similar. As you can see, the y-axis hasn't changed. The x-axis hasn't changed. But what has changed is the bars that represent the number of heads have fattened, have increased in size. And what this is insinuating is that we've gone from a discrete distribution, so in the sense that you have counts that are represented for each bar, and here, and that was in the previous slide, and in this slide we are showing areas for each bar. And so this is an important result because what we're showing is that probabilities can be areas under a histogram. So why is this important? So this is important because for us to be able to consider an area as opposed to counts allows us a little more flexibility in terms of being able to predict, or what's called expectation. So meaning that depending on a distribution of your random variable, you want, as a statistician, the ability to estimate a given probability of obtaining a certain outcome. And to do that, you need the ability to use a function in order to calculate that, which we've just shown in the 2 slides ago. And so the ability for us to use math to do it is what's going to give us the ability in statistics to make these estimations. So in this case, it's really handy that the total area under the histogram or under the Gaussian or normal probability curve is equal to 1. And this is, for us, kind of the start to introducing you to the idea of expectation in statistics.